So here we have a cylinder inscribed or embedded in a cone, a fixed cone. And the fixed cone has a specific size. The cone has a height of 4 and a radius of 3. So as you can see, I'm just moving this around. And the question for today is, what is the size of the volume of the cone? What's the maximum volume of this cylinder inscribed in this cone that we can get from this situation? So when you take this and you can move it around, you can see many different perspectives of the function. I'm sorry, of the shape. So I can take this and looking from the top view. So if you see from the top view, you see two circles, one of the cone and one of the cylinder. And if I tilt this over here, we can see the more 3D view. But if I actually move this from a side, from a cross section, what do you notice here that we had kind of seen before? So right now we can see it's still 3D, but it's just they're taking a cross section of it. You can see that we see a rectangle actually embedded or inscribed in a triangle. And we have done this in the previous video. So the approach for this question to optimize the volume of the cylinder is very similar to that video. So we're going to maximize the volume of a cylinder. So let's start off with the equation of the cylinder. So the equation of a cylinder is V is equals to pi r squared h. And then what we're going to optimize, you're going to have to make a choice whether you're going to express volume in terms of r, or volume in terms of h, or maybe volume in terms of another variable that's connected to the dimensions of the shapes involved. So let's actually label in the 3D diagram, the radius and the height. The height is from the top of the circle to the bottom of the circle. So that's the height of the cylinder. The radius starts from the center and over here. So I'm going to use the bottom one. This can also be the center. That's the radius. So these are the radius and this is the height. Now, if I take this shape in 3D and cut it in half. So imagine me taking this and cutting it exactly two equal pieces. What we see here is the cross section. So this becomes a 2D. And how are the radius and height related? Well, we know that this square here, or this rectangle shape here, is the cross-section of the cylinder. This triangle here is the cross-section of the cone. So let's actually label what we know. So I'll use blue. So from here to here, this here is the height of the cylinder. This here is the radius of the cylinder. So what we see here is that, there's another thing we need to know. From here to here is actually the height of the cone. And from here to here, I'll use yellow, it's going to be always 3. So 4 and 3 never change because the cone is fixed. And the way that we're going to approach is very similar to another video on rectangle inscribed in a triangle, where we're going to be using similar triangles. So imagine you have the big triangle. I'll call this A and B and C, and I'm going to call the top triangle. So you see there's 3 triangles in here. There is the big one, A, B, C, outlined by the yellow, and then we have the top triangle and the bottom right angle triangle, and they're all similar because they all share a right angle triangle and they share common angles based on the corresponding angle theorem. So let's just label this triangle. It's A, B, C, and then we'll call it A, we'll call this D, I'll call this M, I'll call this N. So in other words, we have 3 triangles. So the big triangle, ABC, is similar to the top triangle, which is AMD, which is similar to the bottom triangle to the right, D and C. And what we're going to do is compare the height and the base. Now, for the yellow triangle, I'll use yellow here, the height, so I'm going to put here H over the base. Now, the big triangle is always 4 and 3. That never changes, 4 over 3. And that equals to, the ratios are going to be also similar to the top triangle, which is something over, now I'll use green here. So this is the height of the top triangle and the base of the triangle. And the bottom part here that I'm scribbling here is actually called R. All right. Now the top one, what is it going to be? Well, if you notice the top hand part, this green part is equal, this green part and this yellow part here adds up to what number? 4. And so what we're going to do is, to get the green part, we're going to take the whole entire 4 and subtract this piece here, which we call H. So this piece here is going to be 4 minus H. So put in green, 4 minus H. And now we have a relationship between an equation. This is our constraint. But what about miss? What about the bottom triangle? So let's look at the bottom triangle over here. I'll use red here. So we know that this is going to be H, because that's the height. This part here, I don't know what it is directly. Oh, yes, we do know, because from here to here is always 3, and if this blue piece is r, then this piece is going to be 3 minus r, 3 minus r. So now we have many ratios that are related to the base and height and base, and these are the constraints. No matter what happens, the ratio is always 4 to 3, 4 to 3. So our constraint has a bunch of choices. Either you want to take these two, the first two fractions, two ratios, and set them to equal to each other as your constraint, or you can let the yellow and the red be together as your constraint, or you can let the green and the red to be together. So you need to make your choice. But I have a feeling if you're going to make the red and the green together, your constraint equation may be a bit more complicated. So I'm going to stick with the first two, the yellow and the green. So if I take the yellow and the green, okay, and I'm just going to do some manipulations with this. So this becomes 12 minus 3h. I'm pretty much cross multiplying, and then here is our constraint. This is our constraint equation. So now you need to make a choice whether you want to express going back to up here. Do you want v in terms of r and v in terms of h? There's a lot of choices, and in this case, I'm going to express everything in terms of r, v of r. If I want to leave the r alone, I'm going to have to replace the h. So in this case, I'll put here, isolate for h. H is going to be equal to, let's bring the 3 over. I'm just going to show you all the steps then. 4r, divide everything by h, so we can get 4 minus 4 over 3r. So this is my constraint. So anytime I see a h, I'm going to replace it with this. So in other words, my equation is going to be pi, which is down here, r squared. But what's h right now? Well, h is going to be 4 minus 4 over 3r. And then I'm just going to expand this. So 4 pi r squared minus, in this case, 4 over 3 pi r cubed. This is our function. We're going to take the derivative to figure out the max value. So now we're going to talk a bit about the restrictions for the radius. So if you look at the bottom left hand side, this is the radius. In order for the cylinder to exist, you need to have a radius. So the radius must be greater than 0. And also there is a maximum the radius can go. So notice the radius of the cylinder is constrained within the radius of the cone. So the radius of the cone, it was established, it was from here to here, it's 3. So that means the radius of the cylinder, this green one here, cannot go past the 4. So in other words, the radius in our case is going to be below 4 and above 0. Now, if the radius was 0, so let's actually point towards here. So if, let's just say the radius of the cylinder was 3. So imagine you taking the ratios, all right? If you put the radius for 3, what's going to happen to the denominator? It becomes a 0, and which means undefined. So the ratios don't work when the denominator is a 0. So that means we're actually looking at the restrictions in the denominator of our constraint ratios here. So remember, r cannot be 0 and r cannot be 3. Oh, so it actually should be 3. This one should be 3. So just go through really quickly algebra, the calculus part. I took the derivative from here to here. I factored, so here factored. And then I'm going to solve for the zeros. The zeros, I'm going to set v of r is equals to 0. Therefore, r is going to be 0 and r is going to be 2. So we know that the radius cannot be 0, but we know that, oh, this is a critical point. As a critical point, because I can sub 2 back into the function, I'm going to get some sort of number there. And then after that, I'm just going to try the second derivative. In this case, I'll take this equation here, take the second derivative. I get 8 pi minus 8 pi r. And then all I do is substitute 2 into the second derivative. And I'm going to end up getting minus 16 pi, which gives me negative 8 pi. And because this is less than 0, I know that this is curving down. It's concave down. So I know I'm going to have a local maximum. And then the last thing we're going to have to do is check the end behaviors, meaning you're going to have to sub in, I want to use sub in. Actually, you should be using limits. What happens is 0 coming from the right of the function. And if you did that, I know I'm going to get 0. And then over here, if I subbed in, if I took the limit from the left, and I'm also going to get 0. And we know that if you figure out this number here will be bigger than 0, 0. We know that this is going to be your absolute max.